Good afternoon. During the lecture of today, we present the notion and properties of geodesics. Suppose that we have a moving particle on a plane, and suppose that the speed is constant and it does not turn left or right. Then it is clear, at least from an intuitive point of view, that the trajectory is a straight line. Now let's ask ourselves what is the trajectory of a moving particle, not on a plane, but if we consider a surface. We always assume that the speed is constant and that the particle does not turn left or right. This condition here that I will call 1 implies that the vector gamma second, if gamma denotes a parameterization of its trajectory, has no component in the direction of the vector gamma prime t, and this condition 2, that I will denote by 2, implies that gamma second of t has no component in the direction of R90 gamma prime t. This is clear. Why? Because if gamma second has a component in the direction of gamma prime t, then we have that the velocity of the moving particle changes, and if gamma second has a component, a non-zero component in the direction of R90 gamma prime t, it turns left or right. So the unique possible direction left for gamma second is the direction normal to the surface, now we are ready to give the definition of geodesic, which arises from these considerations. So definition 5.1, a regular curve in a regular surface S denoted by gamma defined on I with values in S is called geodesic if for every t in I, the vector gamma second of t is a normal vector to S at gamma t. Another term that we will use is the following: geodesic segment is a geodesic whose domain is a compact interval of the form AB, closed on the left and on the right. Let's present the first properties of geodesic. So let S be a regular surface, and let gamma be a regular surface in S. Sorry, regular curve in S. 1. If gamma is a geodesic, then gamma has a constant speed. 2. If gamma is of unit speed then gamma is a geodesic if and only if the geodesic curvature kg t, this is equal to 0 for all t in I. What is the proof of this result? So about 1, we have to prove that if gamma is a geodesic, then gamma is a constant speed. If gamma is a geodesic, we have that by hypothesis gamma second of t is a normal vector to S at p, at gamma t. In particular, the inner product of gamma second t and gamma prime t, this is identically 0 because gamma prime t is a tangent vector but the inner product gamma second t gamma prime t can be written as 1/2 ddt of the inner product gamma prime t gamma prime t. This implies that gamma prime t squared is a constant that is let's write gamma has a constant speed. About 2, we've seen in the past that if gamma has a unit speed, then the acceleration vector can be decomposed as follows: kn n gamma t plus kg r90 gamma prime t. Precisely, we have that the acceleration vector of a unit speed curve on a surface can be written as a normal component and a component in the direction given by r90 gamma prime t. And this is the geodesic curvature. If we look at the definition of geodesic, it is clear that A must be normal to the surface, so this means that this component here must be 0, which happens if and only if AG is 0. This is the end of the proof. Okay, now let's ask ourselves the following question. Do geodesics exist? And secondly, are they unique? And what does it mean for a geodesic to be unique? The answer to this question is provided by proposition 5.3, which essentially says that once you fix a point on the surface and you fix a direction, there exists a geodesic curve having initial point the point you have chosen, and the initial direction the vector you have chosen. So let S be a regular surface P point of S, V a vector in TPS with length of V denoted by R different from 0. Then there exists a number that I will denote by epsilon, which is a function of P and R, positive, this function is smooth, such that the following two statements hold true. There exists a geodesic gamma V defined on minus epsilon with values in S, such that gamma V at 0 is equal to P, gamma V prime 0 is equal to V. 2. Any two geodesics with this domain satisfying these initial conditions must be equal. Furthermore, gamma V depends gamma v of t depends smoothly on t, v, and t. So this proposition, whose proof will be presented later, not today, has two parts. The first part is about the existence, and second part about the uniqueness of a geodesic curve with initial point given fixed point and with initial velocity a given tangent vector. Let's make now a remark. Let's observe that it is enough to study only unit speed geodesics. Why? Because all other geodesics are reparametrizations of them. The proof of this observation is very easy. Suppose that u is a tangent vector of a unit length and r is a non-zero number sufficiently small let's ask ourselves if there exists a relation between gamma Ru and gamma U. So this is the geodesic having as initial velocity the vector U, and this is the geodesic having as initial velocity the vector Ru. So so this has initial velocity Ru, and this has initial velocity U. We want to use the uniqueness part of a previous proposition in other terms, if I have two curves with the same initial velocity, the same initial point, then they must coincide. Now, which trick can I use in order to modify, for example, the initial velocity of this curve to make it equal to the initial velocity of this other curve? Simple. Let's look at gamma URT. This is a reparameterization of gamma U. And now the initial velocity is RU, because there is a R here. So this implies that gamma RUT is equal to gamma URT. What about the value of epsilon PR? Can we find a relation between epsilon PR and epsilon P1? Let's maybe recall what is epsilon P1. This is the number which gives you the domain of gamma U. And remember that by hypothesis the length of U is 1. This is why there is a 1 here. Instead, gamma RU is defined on this other interval. So since we have this relation, then if gamma U is defined on minus epsilon P1, this means that RT belongs to minus epsilon P1, epsilon P1. What can you say about the domain of gamma RU? Simple. Epsilon PR is equal to epsilon P1 divided by R. Why? Because this implies T varies in minus epsilon P1, where both these numbers are divided by R. So if, for example, R is larger than 1, the domain of definition of gamma RUT shrinks if compared to the domain of definition of gamma U. Now let's see some examples. The first one is geodesics in the plane a regular curve gamma in R2 is a geodesic if and only if it is all or a portion of a straight line. And remember what we said before, it's not enough to be a straight line because we have to be sure that the acceleration vector satisfies some conditions. In particular, we want gamma second must be orthogonal to R2. And in order to have this condition satisfied, we will see in a moment that the line must be parametrized by parameterized at constant speed. The reason why this is the good parameterization is that since gamma t belongs to R2, then gamma prime t, gamma second t belongs to R2. So in order this to be true, gamma second t must be 0, which implies gamma prime t equal constant. Example number 2. Geodesics on the punctured plane What is a punctured plane? It's a plane for which we remove some points. In our case, we remove just one point. So consider R2, from which we remove the origin. This is our surface S. It is possible to prove that S is a regular surface. So we can work on this surface exactly as before. A regular curve in S is a geodesic if and only if it is all or a portion of a straight line parameterized at constant speed. There are two differences with previous example. One, if you take, for example, two antipolar points, P and Q, then there is a non-geodesic joining them. Second, in the previous example, the value of epsilon P1 was plus infinity. No, sorry. Okay, was plus infinity in the sense that if you take a point P over R2, then there is a geodesic gamma U T such that gamma U0 is a P, gamma prime U0 is U, and this is defined on minus infinity plus infinity. What happens if what happens if I work in S equal R2 minus the origin? So suppose that this is origin, and you take P, you choose P to be this point, then suppose that you choose U to be the vector P over length of P. Let's ask ourselves what is the value of epsilon P1. Why 1? Because the length of U is 1. So we are looking for a geodesic passing by P having as initial velocity vector U. It is clear that the geodesic has to stop here because there is a missing point. So clearly epsilon P1 is equal to the length of P, because if we travel along this straight line for a time equal to the length of P, we will reach the origin, which is missing. Example number 3, geodesic in the sphere. Consider the orientation given by this normal unit field. Let P be a point of S2 and V a vector in TPS2 of length 1. Then consider the curve gamma T defined in the following way. This is a curve which is clearly defined on R and takes value in S2. And let's ask for ourselves if it's a geodesic or not. In order to check that this is a geodesic, we have to prove that the gamma second is a normal vector for any t. But gamma second is minus cosinus of t, p minus sinus of t, v, that is minus gamma t, which is also equal to minus n at gamma t, implies gamma second t is a normal vector. So gamma is a geodesic. I want to make a picture. So how does this curve look like? So suppose that P is, for example, this point, and V is this vector. orthogonal to the blackboard. Then, since gamma t is defined this way, we have a linear combination of P and V. So this means that gamma t belongs to the plane given by the span of P and V. And this curve looks like this. So it is clear that if I change V, so there exists one geodesic for each vector V. So this means that any pair of antipodal points T minus P on S2 are joined by infinitely many geodesics. Special case, T equal North Pole, which implies minus P equal South Pole, like in the picture. The sphere also shows that there exists another phenomenon. Let's make another picture here. Sorry, I'm not satisfied with this picture, so I will try again. This is better. So suppose that I take the geodesic joining these 2 points. This way. Clearly, this geodesic is not the shortest curve joining its endpoints. And this kind of phenomenon does not occur on the plane. It is instead the geodesic which is the shortest curve joining its endpoints. Now another example. if I'm not wrong, is example number 4. 1, yes, number 4. Geodesics on the cylinder. For the sake of simplicity, we consider the cylinder of radius 1 with the vertical axis given by the z-axis. Let's choose the orientation n given by this formula. Okay, let's consider this kind of curves. Consider the helix gamma t given by cosinus of t, sinus of t, ct, where c is a number in R. This curve has an initial point given by 1, 0, 0, and initial velocity given by 0, 1, c. So this means that if this is the cylinder, this is the point P, and this is the vector. Let's put some letter X, Y, Z. This is a vector gamma prime 0. So if C is 0, we have that gamma t reduces to cosinus of t sinus of t 0. This is the parameterization of a unit circle passing by P. In this case, the tangent vector, the initial velocity vector is the yellow curve, and the geodesic is this one. Instead, if C is different from 0, we have that the helix looks like this, and also in this case we have that this kind of geodesics are not the shortest curves between their endpoints. So for example, consider the point Q given by the intersection of a vertical straight line and the helix. So this segment of geodesic clearly is not the shortest curve joining P to Q, because the shortest curve joining P to Q is this one. It is possible to prove that these vertical lines are geodesics. So the curve 1, 0, t, for example, is a constant speed polarization of the vertical geodesic passing by P. This curve does not belong to the family described by the formula gamma t equal to cosinus of t sinus of t ct, but it can be seen as a sort of limit configuration of this when c tends to infinity. If c tends to infinity, the initial velocity vector of the helix tends to become vertical. Okay, let's talk about the Clairaut theorem. I will not present the proof of this theorem. I will just present this result briefly. In general, it's very difficult to describe the geodesics of a surface, but there is a large family of surfaces for which there is a relatively easy description. They are the surfaces of revolution. Maybe it's a good idea to recall what is a surface of revolution. So we introduce the surfaces of revolution in example 3.25, page 131. Essentially, we consider a curve having this form, for which the functions x and z satisfies the following assumptions: x prime of t is positive, and z prime of t is positive for all t in AB. Then we define a surface of revolution as the geometric object that we get if we revolve gamma, the trace of gamma about the z-axis. The theorem says that theorem let S be a surface of revolution and let beta denote a unit speed curve in S for every S in I let rho S be the distance from beta S to the axis of rotation and let psi of S in 0 pi denote the angle between beta prime S and the longitudinal curve through beta S. I will show you a picture later. One, if beta is a geodesic, then rho S sinus of psi S is a constant on I to if rho s sinus of psi s is constant, on I, then beta is a geodesic. So this is the converse of part 1. Provided that no sub-segment of beta coincide with a sub-segment of a latitudinal curve. So let's try to make a picture. Okay, this is approximately a surface of revolution. This is the z-axis. Okay, so suppose that this is this is beta s. This is a trace of beta s. Let's fix this point. Then rho s is this distance. And what is psi of s? Psi of s is the angle made with the longitudinal curve passing by beta. The longitudinal curve is essentially given by the intersection of S, which is our surface, with a vertical plane containing the z-axis. If you want, you can also say that it's the curve that correspond to the value theta equal to constant. Okay, let me find the formula for you. I have it somewhere. Essentially, we said that the surface patch for this kind of surfaces looks like this. A longitudinal curve is the curve you get if you consider the map T sigma theta T with theta fixed. I think it's easier to say that a longitudinal curve is the intersection of S with a vertical plane. So let's mark this curve using a blue color. For example, this one. So this is the tangent vector. This is beta prime. And this is the angle psi. So the theorem says that if beta is a geodesic, then rho s times the sinus of psi s is a constant, and vice versa. If this function of s is a constant, then beta is a geodesic. I want to make the following observation. Why we look at longitudinal curves? The answer is this: every longitudinal curve is a geodesic if parametrized at constant speed. Why this is true? Because along longitudinal curve, psi s is 0. That psi s 0 implies rho s sinus psi s equal 0. And the other thing I want to say, why the second statement of Clairaut theorem says that says that if rho s sinus psi s is constant and beta, a subsegment of beta does not coincide with a latitudinal curve, which is this latitudinal curve, that is the curve you get if you consider this map. Is that most of the latitudinal curve now let's write is this. Most of the latitudinal curves are not geodesics. Precisely, it's possible to prove that the value t that we have to choose in this formula, for which you get a geodesic, is the one for which x prime t 0 is 0. So this implies theta sigma theta t0 is a geodesic. So what are the geodesic in the picture I made? This one, and this one. Let me check how much time I have. Okay, let's say that let's recapitulate. For a surface of revolution, the geodesics are the longitudinal curve, and this follows from Clairaut theorem, and only the latitudinal curves for which you have a critical point for the function x of t. We will prove this later. So that's all for today. Thank you for your attention.